begin in search for the truly, really elementary particle. Now, are you competing with Halloween today or something? I don't know. But it shows that you really, truly want to know the truly, really elementary particle. Now, it's my pleasure to welcome you to this session of revolutions. Usually revolutions are not welcoming events. Usually they are messy and turmoil, and you have seen that on the TV at least. But these revolutions are far more reaching and far more important because it is kind of changing the paradigms, changing our lives in a sense. Look at this generation who is doing all the time this thing, while 5 years ago or 10 years ago they were doing something else. And I wouldn't take much talking about the revolutions, but this is part of the first Eastern Illinois University Symposium on Science and Technology, and Dr. Stephen Daniels and myself wish that it will be the last, but it is just the start. And I wish that some of you will take the torch or the baton and do the second, third, the fourth, and the 50th, so that you bring your grandkids here and say, hey, remember this 50 years ago, we attended this, we were part of this. So, with that, I'll ask Dr. Stephen Daniels to introduce our distinguished speaker.
Well, welcome.
Thank you.
Wow. Thanks to the stage left. Welcome, everyone. I'm glad that you could make it to this installment of the Revolutions in Science and Technology Paradigms. Today we'll be hearing from Britney Rutherford, our academic support professional in the physics department. We were very pleased to, she's a new hire for us. We're very pleased to have her here as she, among other things, has come from Fermilab. So she does have some expertise in this area. I look forward to hearing what she has to say. So with that, I will welcome Britney.
So today I'm going to be talking to you about the search for the truly elementary particle. And we're going to see how far we can get into the structure of the atom. It kind of seems like for centuries, ever since the existence of humans on this planet, we've been asking questions about, what is this? What is everything made of? Why are we here? And how do these things behave? And how can we describe them with mathematical functions? That's kind of what physicists do, is we just try to get to know things, really, as best as we can. And in this search, always, obviously is going to come up, what are we made of? So let's just kind of get caught up. Most of my talk is going to focus on the 1900s. That's when a lot of these kind of revolutions were formulated. But let's go ahead and kind of get caught up a little bit. So what is an elementary particle? What do we mean by that? It's something that contains no measurable internal structure. So you can't break it apart into smaller pieces. Okay, so we're all on the same page. A long time ago, the Greek philosopher Democritus named the smallest unit atomos, meaning not able to be cut. So this is where we get kind of our primitive idea of what an atom is. By the 18th century, Lavoisier said that all substances are made up of chemical elements. So that's a pretty neat paradigm shift in and of itself. By the end of the 19th century, where I'm going to kind of start my talk, we have Newton's laws to describe motion, which is kind of classical mechanics. A lot of you know about those kind of things. We have Maxwell's equations uniting electricity and magnetism. We have Mendeleev's periodic table of the elements, which is kind of a huge deal, right? They discovered, well, they thought about atoms, and then they thought about all these other elements that are comprised of atoms. And they noticed that we can arrange these elements in a table that makes sense. And we categorize them according to their physical properties, their masses and what they're made of. So this is something that that predates our modern idea of where I'm going, which is our standard model of how we categorize atoms. We also have Becquerel's radioactivity, and from Röntgen we know we have X-rays. Okay, so this is where we're at. This is where I'm setting the stage. Now, in 1897, which really isn't that long ago, if you think about the scope of human history, J.J. Thomson finds the first subatomic particle and calls it the electron. Now, what he does is use this cathode ray to accelerate some sort of charged particle. He called them just cathode rays, through an electromagnetic field. Here, we've got a kind of electric field here and changing magnetic field here, and knowing how much those electrons were bent because of those fields, he could then measure the charge to mass ratio of this newfound thing that he didn't really know what it was. But what he found is that he had discovered something that has a really strong charge and a really small mass. And he measured that charge to mass ratio pretty precisely. So given that he had discovered this new kind of thing, this thing that he's actually detected that he can put his thumb on, he surmised a model of the atom, which he called the plum pudding model. I don't know if he called that, but we call it that now. Which is basically just, he said that this is what an atom is. It's kind of a pudding-like substance that's mostly a positive charge, and then it's got these little kind of balls of negative charge throughout it. And how did he know that the pudding stuff had to be positive? Well, because he knew that atoms were going to come out neutral. So if you're going to have something that's negatively charged, you have to have some positive charge in there someplace. And that's not a completely insane idea, but we do know now that it's not completely accurate either. In 1911, Ernest Rutherford discovered the atomic nucleus, which was basically, we can call him our father of particle physics. Because what he did was he discovered the nucleus of the atom using a scattering experiment. And this is kind of our method now that we use for discovering, smaller constituents of matter. We slam atoms into other atoms and see what happens, see what comes out, see how they collide. And very similar to how you would break up, a triangle of pool balls playing a pool game, he shot alpha particles, which is just ionized helium, through a slit to a very thin gold foil. And what we know of gold is that it's really big, right? It's a big atom. So if we had this model of the atom, which was kind of the prevalent model at the time, what you would expect is that some of those alpha particles are going to bounce off of some of those electrons, and you should get kind of a wide distribution of things. But what he found was that most of the alpha particles that he shot through the gold foil passed directly through. Most of them passed through, which was kind of weird for him. But the ones that did bounce back at really strong angles. And what he had said was this was kind of like firing a pistol at a piece of tissue paper and watching it bounce back. Okay, it was kind of unexpected. And so it kind of makes you think about what's in this gold foil, what's in these atoms that explains this behavior. And what he says is that for the ones that passed straight through, more or less, that tells us that most of the atom is empty space. But what is there is very dense, very heavily charged, and then it's surrounded by those negative light electrons. And then he also said that the lightest nucleus, which is the hydrogen, we'll call that the proton. That came from Rutherford. So from there we have kind of what we described as our modern-ish view of what an atom kind of looks like. It's very quantum mechanical, but we've got pictures anyway. In 1914 we have the Bohr atom, but this, at Bohr's time, was more or less just kind of a dense positive nucleus. It was kind of a ball of confusion. In fact, it wasn't until 1932 when the third elementary particle, the neutron, was discovered. And this was kind of an interesting discovery because they had expected it this time. They noticed that for the three lightest elements on the periodic table, hydrogen has 1 electron and 1 proton. Helium has 2 electrons and 2 protons, so it should weigh twice as much, but it doesn't. It weighs 4 times as much as hydrogen. And then lithium, where we know it has 3 electrons, it should have 3 protons. It should be 3 times as heavy as the hydrogen, but it's not. It's 7 times as heavy. So there's got to be something else in there. And so using a classic Rutherford scattering experiment, J. Chadwick discovers the neutron while bombarding beryllium with alpha particles. And then Werner Heisenberg declares the neutron and the proton 2 manifestations of the same state that we call the nucleon. That's very mathematical. I won't get too much in depth with that. But, so now we have a proton, a neutron, and an electron. So that brings us up to kind of general knowledge, what most people think of as what an atom is. But there's more. There's light. How does light fit into this pattern? Is light a wave, or is light a particle? Because if light's a particle, what does that mean for our search for the elementary particle? Is that elementary? We don't know. In 1801, which is kind of earlier on in these particle physics experiments I'm describing, we have Young's double slit experiment, which, as you can see here, just shows that if you send a light source and some light waves through a single slit, it comes out as a very well-behaved waveform. And then you can split it up into two slits here, so you have two very well-behaved waveforms coming out. And these waveforms will interfere with each other. You guys have seen, I mean, this is kind of just hand waving it, I guess, a little bit, but you know that a wave kind of looks like this, right? Well, if you have a wave that's in phase with that, and you add them together, it's going to come out as one of these bright spots here. But if you have a wave that is out of phase, like that, they interfere destructively, which gives you the dark fringes. So this double slit experiment here just kind of solidified the idea that light's a wave. So, I mean, that's pretty clear. And 19th century Maxwell tells us mathematically that the energy of light is proportional to its intensity. It's a wave, it should be a continuous spectrum like this. And if you have a more intense light source, a brighter light source, you have more energy. But that's not exactly true either. In 1887, Hertz performed the photoelectric effect experiment, where he saw that if you send radiation into a piece of metal, and the metal has a sea of electrons in it, you can bump some of those electrons out of the metal. And it wasn't quite clear at the time what was causing this. All they knew was energy in, energy out. Radiation in, electrons out. And then we have quantum mechanics. And this is where the biggest paradigm shift in particle physics, I think, comes from. Because we know that using Newton's classical mechanics, we can't really describe the way that light behaves. And we can't really describe the way that atoms behave. In fact, Newton's classical mechanics really break down when we're talking about really small things or really fast things. So quantum mechanics steps in. Einstein gives us special relativity, which tells us that space and time can change in different reference frames. It also describes behavior of particles moving at high velocities. And most importantly, E equals mc squared, which just means that mass and energy are two forms of the same thing. So if you read this equation one way, and we say that we can take a little bit of mass and turn it into a lot of energy, that gives us the atom bomb. If you read it the other way, and say you can put in a lot of energy and get out a little bit of mass, that gives us our large particle colliders, where we slam atoms into each other and get new particles out. So this is a very revolutionary equation. Of course, you guys have all seen it. And then kind of briefly, in 1926, Schrödinger told us that at the atomic scale, Newton's laws of classical mechanics give way to mathematical functions that describe particle behavior in terms of probabilities. Now this is a big deal, because this means that we can use math to find new particles. We don't need to see something and then delve deeper into it to figure out how it behaves. We can actually predict that it's there and figure out how it behaves based on math, and then go look for it later. So that gives us a big shift in particle physics. And then, of course, uncertainty principle telling us we can't precisely know both momentum and position of the subatomic particle makes us feel like we have a lot of work to do. Okay, so let's get back to the photon. We were talking about light being a wave, but in 1900, Max Planck proposed, and it's the exact same photoelectric effect, different sort of analysis though. Planck proposed that electromagnetic radiation, the stuff that we're sending into metal to make electrons pop out, comes quantized. Max Planck didn't really have a reason for this. He just kind of proposed it. And he said that this radiation comes in discrete packets where the energy is equal to h, which is Planck's constant, it's just a number, it doesn't ever change, times the frequency of the light. Which is weird because Maxwell had told us that energy is related to intensity. And here we're seeing that energy is related to frequency. So that's completely different, actually. That tells us that the energy depends on what color the light is, not how bright the light is. So in 1905, Einstein analyzed this. There's an equation here, it's a little thin. And Einstein tells us that this process depends on the frequency of the light, not on the intensity. So depending on what color light you send in, what the wavelength, what the frequency of that light is, that'll determine the energy at which the electron pops out. So the photon is described here as a particle. So that's crazy, right? We have the neutron, we have the proton, we have the electron, and now we have light. So that sets us up in a good place, right? We covered everything, right? No, not exactly. In 1924, the Compton effect, I'll kind of skim over this, it's not huge importance in this talk. So Compton kind of did the same sort of scattering product where he slammed an incident photon directly into a target electron at rest. You have a recoil electron that comes out, and then you have a scattered photon of a different frequency. The photon changes frequency. So that kind of supports the idea that some energy is going to be lost in the collision, some energy is going to be transferred to the electron, and you'll get something out that has a different sort of energy. So after this experiment, we can really see that the quantum of this electromagnetic radiation are photons. And they come out in discrete packets of the energy described by Planck and by Einstein. So we can say that these electromagnetic interactions are mediated by an exchange of photons. So that allows us to say that a photon is a force-carrying particle, the first of its kind. So that's very exciting. We have force-carrying particles, massless. Oh, wait, there's more. So after knowing that there are protons, electrons, neutrons, and photons, in the 1930s through 60s, three great ideas complicate this model. We find out that there's more to the picture than what meets the eye so far. We have Yukawa's meson, Dirac's positron, and Pauli's neutrino. We throw a wrench into the whole mix. So mesons, 1934 and 1947. They were predicted, but they didn't yield the results that we necessarily expected. In 1934, Yukawa proposed a mediator for the strong force. We know that the strong force is what keeps a nucleus together, right? But we don't know why. We don't know how. We know that it's a force, and if the electromagnetic force has a force-carrying particle, then why shouldn't the strong force have a force-carrying particle? So Yukawa in 1934 said that we should have a mediator of this force, a quantum for this force, and he estimated the mass to be 300 times the mass of the electron and 1/6 the mass of the proton. So it's kind of in the middle of the weights there. So he called it a meson, meson meaning middleweight. And from there, we say that the electron is a lepton, meaning lightweight, and the proton and neutron are baryons, which are heavyweights. Now it turns out that these terms, baryons, leptons, and mesons, are not unique to electrons, protons, neutrons. There are a lot of baryons, there are a few leptons, and there are a lot of mesons. So that's kind of where we're headed. After 1934, when he proposed this particle, physicists kind of took a break to take part in some less savory physics. And then we return. In 1947, cosmic ray experiments produced two middleweight candidates for the Yukawa meson. So cosmic rays are just kind of those rays that are bombarding us from outer space all the time. We have detectors that we can catch these kinds of collisions with. This is one of those, it's a photographic emulsion exposed to cosmic rays at high altitude. And you can see a pion decay and a muon decay in here somewhere. I can't really read them, but these are decay tracks left by them. And he found two candidates. The pion which turns out to be the true Yukawa particle that he was looking for. It interacts with the nuclei, and it's produced in great numbers in the upper atmosphere, but it normally it disintegrates long before reaching the ground. So that's why it didn't fall under our radar sooner. We just don't see them very much. We see their decay products, but we were never really looking for them. And then there's this other one called the muon. It's lighter than the pion. It lives longer, but it's an imposter. It has nothing to do with the strong interactions. We were not looking for this thing. Where is it coming from? We don't know. It behaves more like an electron, so we'll put it into the lepton family, but it's heavier than an electron. So what is it? We don't really know, or we didn't know at the time. We now know that it's basically just a heavier form of an electron, and another one of the leptons. But physicist Rabi famously quoted, "Who ordered that for the muon?" Because that was one particle that we just found without really looking for. And it's very important, though, in high energy particle physics, the understanding of muons is very important. 1930 to 1956, we discovered antiparticles, which some of you may, if you've seen like Angels and Demons, they have like antimatter in there. It's true that when matter and antimatter come to contact, they do annihilate each other. I don't know if it would end the world or not, but we won't. So in 1927, we have the Dirac equation, which gives us the relativistic energy of a free electron. You can't really see this very well. But we know the energy of just kind of a free electron pretty well. And we can describe electrons pretty well. Well, in 1932, in the cloud chamber, which is just another sort of scattering experiment for high energy particle physics, we discovered that there's a particle that looks very, very much like an electron, but it bends the opposite way. It's got the same mass as an electron, and it's got the same charge as an electron, but the charge is positive, not negative. So it's basically like the mirror image of an electron, and we call it a positron. It is technically an anti-electron, but we call it a positron. So that kind of begs the question, if matter and antimatter annihilate upon contact, then why is there so much more matter in this world than there is antimatter? And that's a problem that's still being kind of discussed and figured out today. Okay, so we've got mesons and we've got antiparticles, and now we're going to throw another one into the mix, the neutrino. The neutrino is very well predicted. In fact, we have to predict it because we can't see it. It's massless, and it kind of goes through any sort of detector that you can throw at it. In 1930, we had this beta decay problem, which means that if you have kind of a heavier nucleus A, and it decays into a lighter nucleus B, and emits an electron, we know that, okay, B is positive, electron is negative, that conserves charge, that's great, but there's missing energy here. If we do our energy conservation equations, and we know very well the free energy of an electron from Dirac's equation, we shouldn't be missing energy, but we're missing energy. So that kind of begs the question, is there something else there? Is there something else carrying away that energy? And it turns out that in fact there is. And it can be described by this equation here if we postulate a new particle. A neutral neutron plus decays into a positive proton, a negative electron, an electron of water, and waited for a neutrino to come along and give them the neutron and electron that they knew had to be there if the neutrino existed. So they actually experimentally found it by looking at the results of its collision, right? So now we know that, okay, energy is conserved and charge is conserved, but there's one more thing that we have to conserve. Because in interactions like this is an electron neutrino, and there's also a muon neutrino. And I haven't talked about the tau lepton yet, but there's also a tau neutrino. So we come up with a new conservation number. It's called lepton number. And we know that in these interactions, lepton number is also conserved. And it's a positive 1 for electron, muon, and neutrino, negative 1 for a positron, positive muon, and an antineutrino. So at this point, I'm not going to go through all of this. This is just to kind of give you a view. We start getting all sorts of new particles popping up. And now that our kind of primitive model of the proton, the neutron, and the electron has kind of given way to the fact that, wait, there's a lot of other stuff out here, we're kind of craving some sort of model. How can we organize this information? How can we make sense? We know that things conserve energy, they conserve charge, they conserve lepton number, they also conserve baryon number. That's another one that they conserve. So we're looking for a way to organize these things, which gives way to the eightfold way, which was kind of brought up in the early 1960s as a way to organize subatomic baryons and mesons into what they call octets. It's just a geometrical pattern that helps you kind of make sense of the way that these particles relate to each other. So this is a meson octet, this is a baryon octet, and the way that it's arranged is so that Q stands for charge here. Everything along this line has a charge of -1. These are all neutral charge. These are all +1 charge. And then S here stands for something else called strangeness, which I'm going to get to in a minute. We discovered some particles that have something called strangeness attached to them. And all the particles here have a strangeness of 1, here have a strangeness of 0, here have a strangeness of -1. So this is very organized, but it gets very complicated very quickly. And now that we know that there are all these different particles that have all these different properties to them, can we break them down even further? And it turns out that we can. And this is the big revolution in particle physics, is the quark model. In 1967, Bellman and Zweig independently proposed that all hadrons are composed of even more elementary constituents, quarks. Okay, so they come in 3 types in 1964. They came in 3 types: up, down, and strange. Something called a strange quark. And then they also, each flavor comes in 3 different colors: red, blue, and green. And color is also conserved in decay interactions and things like that. So if you can imagine, a proton is actually made up of 2 ups and a down quark. A neutron is made of 2 downs and an up quark. And in fact, all baryons are made of 3 quarks. That's how you know it's a baryon, as it turns out. Mesons, on the other hand, like the pion, are made of a quark and an anti-quark pair. And if you notice all of these, we've got ups, and we've got downs, and we've got stranges, and then what is this? This is a new one. This is a C. And C stands for charm. That's another quark that we found. There's the up, the down, the strange, and the charm at this point. But the charm has an interesting kind of story here, this J-psi particle. In 1974, in November, C.C. Ting at Brookhaven observes what he calls a J meson. And by observes, I mean it was another scattering experiment. And the J meson is made up of a charm and an anti-charm quark. Now notice the dates here. In the same month of the same year, Burton Richter at SLAC observes the same particle, but calls it the psi meson. So what do you do when 2 people publish information at the same time? You just kind of combine them, and now we call it the J-psi particle. Unless you're at Stanford, you call it the psi, and if you're at Brookhaven, you call it the J, because they've got their loyalties. But we call it the J-psi. In 1975, another particle was discovered called the upsilon, which is a bottom and an anti-bottom. Okay, so that's another quark, the bottom quark. And then in 1983, there's the discovery of the intermediate vector bosons, the W and the Z bosons. And what those do is they're kind of the particles that mediate the weak force. Okay, so hopefully I'll make more sense out of that in just a moment. We've got 4 fundamental forces. We've got gravity, we've got the weak force, we've got the electromagnetic force, and we've got the strong force. And at this point in time, we've got the photon, the W and Z bosons. There's 2 W bosons because they come in positive and negative charges, whereas the Z is just neutral. And we've got the graviton, which is highly theoretical to describe gravitation. And then for that strong force, we now have something called the gluon. So if we go back to, let's see, this quark theory model where we've got kind of a proton here with 2 ups and a down quark, That's not all that's in there. In this empty space in here, there's a lot of little gluons holding this all together. Okay, and there's also virtual particles that kind of pop in and out of existence, but I'm going to skim over that for now. It's kind of abstract. So the discovery of the W and Z bosons is really important because we find ourselves now at a place where we're still trying to unify these four forces into some sort of unified theory of physics. And the W and the Z helped us to unify the weak and electromagnetic forces. And sometimes now we just refer to it as the electroweak force. But this is still in the works. Okay, so just kind of a review. We've got some baryons and antibaryons. These are some main ones that in the quarks that they're made of. They're electric charges and spins. And the mesons are the quarks and the antiquarks. Won't spend too much time on that. And we've got, we can describe the forces pretty well with the particles that we've discovered that mediate them. And this is kind of our primitive-ish standard model. Okay? So we've arranged matter into three generations. The up, the down, the electron, neutrino, and the electron are the ones that we see most often on our planet. Okay, the other ones are a little more difficult to come by. We've got this charm and the strange, and the top and the bottom quarks. The top was discovered at Fermilab in the mid-1990s, I believe. So we've got 6 quarks. We've got 6 leptons, the electron, the muon, and the tau, and their respective neutrinos. We also have 4 bosons, the force carriers. And at this point, this is our periodic table, you know, or our analogy of the periodic table. Okay. But there's one missing piece, the Higgs boson. So a lot of you have probably heard of the Higgs boson. Some people have called it the God particle. That was just a coin termed by the publishers who were trying to sell Leon Lederman's book on the topic. And he wasn't really a fan of the name, but they gave it to it anyway to sell the book, and now it's what everybody knows it as, which is kind of weird. But I guess if you think of it as like God said, let there be light, and there was photons, God said, let there be mass, and there was the Higgs boson. Okay? So the Higgs boson is the particle that is responsible for giving things mass. And it's a scalar field. It permeates the entire universe, and every particle feels the field, but it's affected in different amounts. Okay? So it's kind of an abstract idea, and it's not something that we've seen before, but it's something that we know it has to be there. How do we know it has to be there? Because the math says so. Okay? So some of you upper-level physics students have heard of a Lagrangian, right? You can describe particles and their behavior based on their Lagrangian. Well, this is the Lagrangian of the standard model. Don't look too closely, there might be a mistake. I'm just kidding. So these 2 parts here, that's where the Higgs boson comes in. That's how we know there has to be a Higgs boson. But why do we care? Why do we care about the Higgs boson? We've got the standard model of particle physics. Why is it so important that we add another thing to it? Well, it's going to get a little technical here, but the Higgs mechanism is a non-zero field which generates mass and permeates the universe. We know that the W and Z bosons gain mass through degrees of freedom of the Higgs field. The Higgs field gives the W and Z bosons mass. In fact, everything mass. But there's an anti-symmetry there that we don't quite understand. Why is it that the W and Z bosons are so massive while the photon is massless? I mean, we've unified electricity and magnetism and the weak force. So why is it so different? Why are the W's and Z's so heavy when the photon doesn't have any mass at all? The Higgs boson or Higgs mechanism explains this. We know that the electromagnetic and weak forces unify at high energies, but this symmetry breaking, the electroweak symmetry breaking as we call it, this occurs at low energies, so everyday energies. Actually finding the Higgs meant that our prediction, our theory for the origin of mass is confirmed. And some of you may know, it was recently found And I'd like to take a minute to discuss how it was found, because I feel like that's kind of an interesting ending to this talk, to bring us to the Higgs boson. It's kind of a missing link of our standard model of particle physics. And it's very current in the news, very recently, actually. So we have two machines capable of studying the Higgs boson. Well, only one is up and running now. We have the Tevatron at Fermilab, and I worked on this for a couple of years. And basically, and then there's the Large Hadron Collider at CERN, which is running now. And the Tevatron kind of shut down so that the LHC could take over, because it had much higher energies and much greater sensitivity. But they did very similar things. Basically, what they do is they, around these rings, they speed up protons to close to the speed of light. Okay, so that gives them a lot of energy. And what do we know? We know that E equals mc squared. So if we have a lot of energy and we collide these particles together, we're going to get some mass out, right? And it's going to be actually kind of exotic masses that we've never seen before, masses that are produced way out in the galaxy that we just don't get on Earth unless we do things like this. So when they smash together, there are very specific points where they smash together. They smash in the center of these huge detectors. This is the collider detector at Fermilab, which is no longer in operation, and its predecessor, the compact muon solenoid at the LHC. This is much bigger. You can see a little person down here. It's pretty huge. But as you can see, these are kind of cylindrical things, and there are detectors that are kind of in layers. Because when you smash these protons together, it's not just one type of particle that comes out. You don't know what you're going to get. And you need to be able to detect everything that you're going to find. And you're going to need different sorts of detectors for different sorts of particles. So they layer them like an onion. And this is how it works. This is kind of a cross-section of the CMS detector. It starts out with a silicon tracker here. And the electrons here, you can kind of see these colors represent different sorts of particles and how far they make it through the detector before they're detected. The electron goes straight through this silicon tracker and leaves a track in the electromagnetic calorimeter, as do photons. So you can tell if you caught a photon or an electron by looking at the electromagnetic calorimeter. Charged hadrons like the pion and neutral hadrons like the neutron will decay in something called the hadronic calorimeter. So you'll find that there. You have a superconducting solenoid to give it a magnetic field so that you can trace the bend of charged particles like muons. And by its bend, by its curvature here, you can tell what its momentum or what its charge is, right? So the muons actually go pretty far. They can go all the way through these muon chambers that just kind of detect their tracks and can tell you where they are and how charged they were. And how do we find neutrinos? We don't. We know that there's energy missing from these collisions. We can perform very detailed calculations of where we have missing energy in these collisions just based on conservation laws, and we know that neutrinos are there. These are just some kind of closer pictures of CDF detector elements, the silicon, the outer tracker, the magnet that they use, kind of gratuitous pictures, electromagnetic calorimeter, shower max detector, whatever. Okay. So when we're looking for the Higgs boson, now this is where I'm going to start to get a little bit technical because I want to explain to you how we found the Higgs. But in order to do that, I'm going to have to give you kind of a sample analysis a little bit. So if you want me to slow down, just let me know, but I'm going to try to move quickly so that you guys don't have to be here all night. So before we even start smashing our protons together, we have some theoretical constraints on the Higgs mass. We know from another experiment called LEP that the mass of the Higgs boson has to be greater than 114 GeV. And electroweak theoretical constraints tell us it has to be less than 185 GeV. So we've kind of got this window where we know that the Higgs has to be that gives people an area to search. And when I say this, I'm talking, this is an analysis that was done maybe 5 years ago before we found the Higgs boson. Okay, so keep that in mind. This is what we were working with. By we, I mean particle physicists. We know how the standard model Higgs is produced. And at the Tevatron, it's mostly produced by something called a virtual top quark loop. Okay? And there are other Higgs in association with a W or a Z or something called vector boson fusion. It's way beyond the scope of this talk. But the point is, we know how the Higgs is produced. We also know how it decays. And the Higgs is going to decay differently depending on what its mass is. And maybe some of you guys know this, but when we're looking for the Higgs boson, we didn't know what its mass was exactly. If we could pinpoint its mass, that's when we found it. Okay? So it's important to look at how the Higgs behaves at different masses. Above about 135 GeV, it primarily decays into two Ws, two W bosons that we were talking about. And under 135 GeV, it primarily decays into two B quarks. Okay? So depending on what mass you're looking at, it'll tell you what kind of decay products you're supposed to be searching for. So in this example analysis, I'm going to give you an example signal. Like you saw here on these tables, there are other ways for the Higgs to be produced, there are other ways for the Higgs to decay. But you basically just got to pick away and kind of look for it. And there's a lot of different grad students working on a lot of different channels. But let me just talk quickly about this one. If you have two gluons, form a Higgs, Higgs decays into two Ws, we know that each of those Ws is going to decay into a lepton, an electron, a muon, or a tau, and its neutrino. Okay, and we know from conservation of charge that one of those leptons is going to be positive and the other one is going to be negative. Okay, so when we're looking at billions of collisions per second in these machines, there has to be a way for us to kind of cut out the events, the collisions that we don't find interesting. Okay, because there are a lot of collisions that don't produce anything like what we're looking for. So when we're looking at these collisions and the particles that come out of them, we have to place cuts on what we find interesting and what we want to throw away. And for this particular analysis, we're going to throw away anything that doesn't have two high momentum electrons or muons and significantly missing energy. That's missing transverse energy, MET. The missing energy, of course, tells us that there were neutrinos in there, because that's what we expect. But the problem is that, and the most fundamental challenge, is that this process doesn't happen very often. But there are a lot of processes that happen that give us two leptons and two neutrinos that aren't Higgs boson related. And we call those our background. So we have the events that actually have a Higgs in them that gives us two leptons and two neutrinos. And we have events that actually don't have a Higgs boson in them, but they're still giving us the same products. Okay, so that's our background. And separating the signal from the background is a really daunting task. And there are a lot of highly developed algorithms out there to separate. So for this particular process, we know more or less what kind of backgrounds we're dealing with, right? So we could just have two Ws that didn't come from a Higgs that are still decaying to two leptons and two neutrinos. That's part of our background. That's a huge part of our background. And a bunch of other processes that gives us the exact same signal. It's by analyzing the kinematic properties of these collisions and these decays that we can kind of separate our signal from our background. For instance, one quality would be like the angle of separation between the leptons that come out. Okay, that's going to be different depending on what kind of collision you're talking about. So you can look for two leptons and two neutrinos, but you have to look closer at how those leptons are related to each other and how those neutrons are decaying relative to one another. So, for instance, if you have a spin 1 Z boson decaying into two W bosons, you could get the same signature. But for a spin 1, you get a different separation between the leptons. For the spin 0 Higgs boson, decaying into two Ws, you get a peak right down here that tells you the angular separation of the leptons. And this is actually, this red line represents a standard model Higgs times 10. So it's actually much smaller than that. But as you can see, you can separate them using computer programs and algorithms. You can separate those processes and see what looks like a Higgs event, what doesn't look like a Higgs event. I know this is getting kind of technical, but I'm kind of plowing through. the analysis tools they use, in case you guys have heard of any of these, would be like neural networks, matrix elements, and boosted decision trees. And I can talk to you guys more about those if you're interested, like, kind of you guys one-on-one. The way a neural network works, just quickly, is that you take your data and your signal and all your predictions for what the background is going to look like. You throw it into big black box that you've created. You throw in all your signal, you throw in all your background, and this neural network, which is just a computer program more or less, is able to analyze multiple input variables. And it starts to train itself to recognize different patterns in the data that you're sending it. And the neural network can spit out something that tells you if what you're looking at looks like a signal or looks like a background. It's very easy to distinguish. Okay, so in the end, we know if we found a signal or we know if we found a background, but how sure are we that our results make sense? Let's see, how far do I get into this? This is how we know we found the Higgs, is a plot that looks like this. And I'm just going to kind of skip this and try to explain this to you. This is what we call the money plot, right here. And the money plot is the plot that they show after they've given a 2-hour lecture about something, and the entire crowd is there because they want to see one thing. They want to see your results. They want to see this. Okay? And this is the plot that showed us that we found the Higgs. On July 4th, 2012, when I was vacationing with my family in Wisconsin Dells, I got a phone call saying, "We found it! We found the Higgs." We observe in our data clear signs of a new particle at the level of 5 sigma, which is very, very strong sensitivity. We're very sure of this discovery in the mass region around 126 GeV. Okay, and this is the event that we see that shows it. This is our weighted events that we expect to see, and we see we have a little bump, extra events here at about 126. But this plot, let me see if I can explain this real quick. This y-axis here is the ratio of the Higgs cross-section over the standard model cross-section. And then the x-axis here is the mass of the Higgs boson, so it's different for every mass. Here at 1, we can say anything that's under this line is not where the Higgs boson is. Okay? Everything that's under this line, no Higgs boson there. Okay, so we've got our expected, just basically just what we expect to see with just our background and no Higgs bosons. And then we have our actual observed data here. And anywhere that the observed data is higher than the expected, we're seeing something more than what our background tells us should be there. Okay, so right around here, we're seeing a lot more stuff around 126 GeV than what we would expect to see there without a Higgs boson. And also, every other mass at that point had been excluded. It's not out here, and it's not down here. It's right here. And it's with this plot in summer of 2012 when CMS and ALICE experiments at the Large Hadron Collider in Switzerland found the Higgs boson. Yay, it's very exciting. But it was just like 2 weeks ago, between 2 and 3 weeks ago, that the Nobel Prize in Physics was awarded to Peter Higgs, Francois Englert, for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN's Large Hadron Collider. So now we have our standard model. We have our standard model of particle physics, including the Higgs boson. And yet we don't, because the standard model is just one model, right? Maybe it's not the Higgs that fits into the standard model. There's another model, for instance, called the supersymmetric model, in which there could be 5 Higgs bosons, and the one that we found at the Large Hadron Collider is just one of them, right? So that would throw our whole standard model out of whack. There are also theories that describe a fermiophobic Higgs that only interacts with fermions and not with bosons. And then there's a theory of Technicolor that holds that there's no Higgs boson, but new interactions that generate the masses. So the low mass standard model Higgs searches may be just a first indication of a different model, a not standard model. But we wouldn't know it until the LHC finds the other Higgs bosons. Okay, so in conclusion, I have no conclusion. We don't know. We're still going. Questions?
Just a question about the Rutherford. Any relation between Rutherford?
Not that I'm aware of. Yeah.
Can you back up 3 slides? Over on the right, at about 500 GeV, the experimental results also go above the 1 line. Does that indicate anything?
Okay, good question, good question. It would, except, see, this is about 500. We know from theoretical constraints, before we even started looking experimentally for the Higgs, that it has to be less than 185. So what we're seeing up there is not our standard model Higgs.
What are we seeing up there?
Maybe a different Higgs.
Okay.
We don't really know. It's not the standard model Higgs.
So this Higgs boson is the thing that cannot be separated any further. That would, or supposedly.
I mean, it is technically at this point considered one of the fundamental particles of particle physics. But it's important to keep in mind that that is not the elementary particle. It's actually all of these at this point are elementary particles. That was just kind of our missing link.
Is this shedding any light on dark matter or dark energy?
It absolutely is. I'm not sure exactly how. I do know that that's one of the applications of finding the Higgs boson is illuminating dark matter and dark energy, as well as supersymmetry, extra dimensions, a lot of other really insane physical properties of the universe are being studied now that we know what the standard model Higgs boson looks like.
Do you think it would have been possible to find these results without computers running the data?
No way.
No.
No way.
Yeah.
No, these collisions, when we accelerate the protons and slam them together, they're happening at billions of collisions per second.
Oh, yeah.
So absolutely no way. Without the computer analysis, we wouldn't have been able to find it.
Wow.
Not even close.
Yeah, kind of going along with that question, what are you guys actually doing, like, there? Are you guys just interpreting the graphs that the computers give you, and then, like, can you just run the system and let it run itself? Pretty much.
That's a very complicated question. By running the system, you mean just kind of letting the protons go, letting them go? Well, the protons deplete themselves eventually. So you have to have people kind of in the control room who are repeatedly dumping protons out of the machine, creating new, taking new protons and putting them into the machine. It's kind of an on and off thing. They let it go as long as they possibly can, I'll tell you that. But it does reach a point where they just kind of need to start over because the protons are depleting.
Were you kind of on call when you were at Fermilab?
Oh yeah.
And if something went down,
Middle of the night.
you had to go find what was going on?
Yep, I was very, very intimately familiar with this guy. This is my baby. And I have a lot of memories of just kind of climbing up here, being in here, and fixing broken electronics, because if it's 3 in the morning, they don't care. If that machine's not running, it's wasting money. Yeah, so things need to run smoothly.
What about the gravitron? How would you follow the same process? Because
I really don't know. That's a big mystery at this point.
Now that we've found this Higgs boson, what are we looking for now?
Well, we're just kind of studying how that one behaves, but they're also kind of looking for, I guess, the other minimal supersymmetric Higgs bosons. So, and they have different theoretical masses. They know what these masses should be. And the one that we found here, the standard model Higgs, is one of the lightest, if not the lightest, of the 5 predicted by the minimal supersymmetric model. So they have an idea of where to look.
Did you say millions or billions of billions
Yes.
of seconds?
Yes.
What is the machine that or equipment that shows these data acquisition? How do you see the billions happen?
Well, there's a really complicated trigger system that, as soon as it's detected, if it's a completely boring collision that doesn't contain any information that anybody's interested in, it goes away. So it doesn't save every single collision that happens, but it does have a trigger system that identifies the energy, momentum, physical characteristics of what you're getting out and tells you if it's interesting or not. So then it'll save it. And these are all saved on, I don't know, really, really extensive databases and servers. And you can send this data all over the country. I mean, they kind of have a tier system where, like, Large Hadron Collider is tier 0. That's where the data is coming from. And then you have universities throughout the country and Fermilab, who's a tier 1 system, so the data goes there. And then they can kind of send that data out to other schools and other analysis groups to pick out what they find interesting.
But it is not like something you say 20 million years ago this happened and nobody saw it, something happens in the science.
Absolutely, absolutely.
This something is,
So there are people still analyzing collisions from the Tevatron. Even though the Tevatron is shut off, it's possible that they could analyze their data and improve their analysis techniques too to become more sensitive. And maybe they'll find the Higgs boson with the Tevatron data and say, you know, well, it was there all along and we just didn't find it.
So the two teams that found Atlas and I forget the other one.
CMS.
Are they the only two teams working on it, or other teams and they were the ones that found it or something like that?
Well, they were the teams at Fermilab, but the Tevatron had shut down by that point. They were the two experiments that were looking for it, yes. There are two other experiments on the Large Hadron Collider, but they look for different things. So Atlas and CMS were the two that were expected to find it if anybody found it. But to tell you the truth, there are a lot of the same scientists that were working on the Tevatron that moved over and started working on the LHC. So people say it's kind of competitive between the LHC and the Tevatron. That's not, it's kind of true, but there are a lot of the same scientists working on them.
do you have any undecided students who want to choose a major today? Any other questions?
How does the discovery of the Higgs boson translate to, say, like the average person? How is the Higgs boson going to, I don't know, you know how we discovered electrons and we have electricity, right?
Right.
We discover Higgs bosons.
We have mass.
What does that bring to everybody? Is it so it's more of a theoretical thing for physicists?
I mean, it's not just theoretical, it's real.
Right. The thing for
real.
physicists.
But
essentially.
yeah, it's something that makes the math work out.
Okay.
Yeah. So that we can exist, so that we can have mass.
Now, this slide, when you have all these,
The Lagrange.
the language too, it's all math, all math.
Yeah.
That's one thing.
That's
That's
one
one
equation.
thing.
One equation.
One equation.
So,
Lagrangian equals that.
Do you know all of
Choose
it?
your major.
I have shot memorized that. A big good tattoo though, I think, right? Yeah, yeah.
What we talked about.
Essentially, how the collider works.
Not
So
that one,
it
but-
collides protons, right? So
Yes.
is there like a large, I don't know, like do you store protons somewhere and then so that you can dump it into the machine all the time?
Exactly.
Just have protons sitting around so you put it in the machine.
Not sure how they make them with the Large Hadron Collider, but yeah, they basically just like store protons until they're needed. Fermilab was kind of trickier because they had to make antiprotons. Because, okay, so the Large Hadron Collider collides protons and protons. Fermilab collided protons and antiprotons. Okay, so they actually had to make those, which made it a lot more difficult.
What are antiprotons?
It's the same thing as a proton, but it has opposite charge. Same mass, same charge, just not positive. It's negative. So it's very, very similar to a proton, but just kind of its mirror image.
There was a question
Yes.
somewhere here.
Since the Higgs boson is sort of the giver of mass, so to speak, is it any surprise that it itself has mass?
I don't know. That's a good question. I don't know if it's a surprise necessarily. But yeah, it's interesting. I don't really know how it would give itself mass. But that's probably one of those things that they're studying still now. And there's a lot to still figure out about the Higgs boson, besides just the fact that we found it. A lot of studies to be done on it. That's a good question though. I don't know the answer to it. Yeah.
And why does the quantity of matter exceed the quantity of antimatter so much?
Well, like I said, I think I put that in there. That's something that nobody knows. Okay, that's something.
I
that-
expected you to be answering that at the end of the talk. See?
I'm not that good. No, that's one of the big philosophical physics questions of the day. Why is there so much more matter than antimatter? You don't know?
And does it matter?
Yes, I want to commend you for coming to a lecture while Halloween parties are going on.
There's a lot that you guys could have been doing at 7 o'clock on Wednesday, so thank you very much.
Thank you.
Thank you, Brittany. Great job.